juga tahu makan belum. Kayaknya gue nanya ya, lu taunya dari mana sebelumnya? Dari kebetulan aku lagi di Cina. Kalau lagi ada ada.
Unit camping.
Campingnya sama siapa? Oh segini.
Gue yang lagi
Sama temen. Soalnya ada warna.
Okay. So this is the first lecture of the day, right?
Yes.
We have another lecture in afternoon.
Yes.
Okay. So it's not a good idea of giving any assignments. Okay, next week I'll try to give some assignments to you.
I don't think so.
Short discussions. Okay, actually yesterday morning we have been making discussions on our metal making, right?
Yeah.
So actually we have drawn some conclusion. So mat is a material which is connecting, or what is the keyword? Treasures. And slag will be the destination for treasures. Okay. I have been recording, or I have collected some videos from the industry. Yesterday was not functioning very well. Today, first of all, I have already closed the microphone. Right? So this one I also replayed. So this is very vivid video. So this is the melted house. So this is melted slag. So this is industrial production. So when we are having a normal production process, the slag looks like water, right?
Yes.
Just like the river or the sea.
Yes.
Right, or the sea. And this is burner, natural gas. It's burning. Try to provide some energy, this form of energy. So this is what is happening here. And if we are moving to the next one more time. Checking. This is outside side. This is the wall, actually like this one. And the inner side is a wall, and we have water cooling element, and we have the framework. Right? So the next one, actually, we have different phases. So in this phase, what are you finding?
Like
Same place.
Yeah.
What have you seen?
Bubble.
Something floats.
Yes.
Something solid floats on the
Yes.
surface.
Yes.
Right?
Yes. Like magma.
Looks like
Lava. Magma.
really the eruption. Volcano eruption. And how about this one? Click again. This is the
Oh, it's
picture.
photo.
The picture. One more time. So if we have such a phase, if we are running the slag with such a property, which means the furnace will cool down and frozen. Frozen. Just like water in a bottle, it's frozen and you cannot drink it anymore. Okay. So the viscosity is what we were referring to. And last time, actually there's one more. This is our fancy one. If we are reading it, I'm very proud of this one because this helped us with a lot of solid result. When you are knowing the situation, when you are knowing the process, you are getting very accurate viscosity information. As I mentioned, let's check it. So here, this is rotating, and there's a working tube. It's connected. And this is the viscosity meter, and this is the result. Its temperature is 1380, and we are getting the viscosity. Getting what's viscosity. Okay, one more time. So if we are doing that, so this is rotating, and this is four part. Four part, and in the working tube, there was 1380 degrees C. The temperature is elevated. And this is rotating, so there is a holding force, and it can be calculated. So when we are moving further, so this is actually the furnace is produced in China, but this one this is a controller for the furnace. So a currency for the variation of the furnace in temperature, we are going 2 degrees C. 2 degrees C. And what are we having? There's one more, actually is a small one of the heating. Okay, this is what we were doing, what we are dealing. This is viscosity, Mandarin. Okay. And last time we have already made some discussions with this one, and this is where we stopped yesterday, right?
Yes.
Actually, this is a phase diagram as well. And this phase diagram is usually used by actually very famous professor, Professor Peter Hines from Newcastle University, and Professor Jack Eugene, same team in Australia. And what we are finding here, so when we are reading this diagram, because some of you have the background of metallurgy, material science. So when you are having the background of metallurgy or material science, you may have knowledge about these diagrams, but for the other students, probably not. But let's try to have some short or very brief introduction. So this is liquidus. So in this section, actually, in this case, so when we are moving to the center, so this is fully melted without any solid. There's no precipitations. Once we are lowering down, so this is temperature interval. So if we are at high temperature, it will melt. But if we are lowering down, this is low carbon, right? Moving down, this is low carbon. But when we are lowering down for this one, if we are moving from here, if we are drop temperature, once we are reaching this part, what does it mean? It means we are entering liquid plus solid. There will be some precipitations, it's like water. When you are putting water in the fridge and temperature was 0 degrees C, when the water is pure, you are getting ice particles with some air, right? And if you are lowering down temperature, keep lowering down at minus 10 degrees C, the bottle will be fully frozen. So this is what we are doing actually liquid. So this is fully frozen. And here we have not only one water, we have two components, A and B. And here, specifically, when we are talking about slab, you still have the information from my slide. So when we are talking about slab, especially when we are talking about smelting. So smelting with a product of metal. So this is dominant, or this is Pertemuan, all over the world. Okay, that boy is sleeping. That's what we're doing. You have to attract my attention. Okay. So this is slab. When we're talking about the slab in the smelting stage for matte, so we are talking about iron and silicon oxide. So this is the slab, the major component. And here, when we are talking about A, when we're talking about B, B refers to silicon oxide, and A refers to ferrous oxide. So this is the story. And this is the liquidus temperature for this spec system. So when we are having this one, so liquid is slab. Solid too, it means silicon oxide. This silicon oxide. So this is silicon oxide. And if we are putting this one, we are applying this one to somewhere else, we will have some other result. Because if we are lowering down from here to where in this region, we are having slag and iron oxide. But when temperature is low enough, so we are having A and B, so which is ferrous oxide and silicon oxide. So this is very straightforward information. And actually the key point will be the temperature interval. So when we are at different temperatures, for example, when we are starting from somewhere here, when we are hitting this edge or boundary, we are having 100% liquid, 0%
Solid.
But if we are moving to this part, okay, just like 1 centimeter from the line, so we will have a very small amount of
Solid.
And this part refers to liquid,
Liquid.
the ratio. The ratio. So this length will be the ratio or percentage of liquid, and this part will be solid.
Solid.
And if we are moving downwards to B, so we are having solid. We are having
Liquid.
like 50%, 50%.
50%.
And here, very small amount. So what's the conclusion will be? The temperature will play the critical role in adjusting the ratio of solid. So this is very sensitive. So this is why we have the figure, or we have an objective pushing down the temperature, right? This is low carbon. This is what's safer. But problem will be liquid. Okay. So this is a brief introduction, but we are knowing that this is slag, and we call this slag as slag. And this one will be used in metal making all over the world. There's no options. This is the only one. This is the only one. Okay. And after this one, I want to have our discussions, or I want to lead our discussions to the component A. And you are knowing that iron is our impurities, and we want to remove that. And here, actually, if we are reading, this is iron oxide, this is our ideal thinkings. But iron is so sensitive, and previously yesterday, we still have the metal sulfur oxygen system, right?
Yeah.
We are starting from this system. So when we are starting, let's take this metal as iron. The iron will be having some behaviors. So there will be X. And X will be larger than X larger than 1. Do you agree? When X is larger than 1, which means iron is over-oxidized than 2 plus. It can be 3 oxide. It can also be dioxide, right? 2 plus, 3 plus. Actually, X is larger than 1. So this is the story. And when we are having X, and X is larger than 1, which means FeOX, we are having Q part. It cannot be, we are not using this one directly because this is beyond the symbiotic situation window. So in the symbiotic window of copper making, the maximum one will be this one. So we are at somewhere in the middle. So this is the problem. And you are knowing the temperature. This one, 1300 plus, 1500 plus, right? So this is the problem. And you are knowing that. When we are having the melting temperature for component A, or the melting temperature for component B, the liquidous temperature can be much lower than the single component. So when you have 2, the melting temperature, liquid temperature can be lower. So this is very, very nice. So when we are actually you don't have so much experience. So you are knowing that last winter, are you in CSU? Last winter.
Yeah.
Yes. So when we are having snow, what did we do? We put salt. Good. We put salt. Salt. This is very popular in most part. When I was in Finland as well, they are using trucks. They are spraying their salt on the road before the snow comes. So what's the reason? What's the reason? So this is the water. water, so this will be 0 degrees C, right?
Mm.
And this is salt, right? So it will be minus something. So when we have these two, the liquid temperature will be much lower than what we can match, minus 20 or minus 10. So there will be some window, the water will be flowing. So there's no ice. The ice is dangerous for us, right? So this is the same story. So when we have two components, the melting or the temperature engaging on melting phase is lower than single or individual component. So this is really nature, a beautiful nature. So we are using that. But we are knowing. So 1, 2, 3. The melting temperature for this one is more than 1700. For this one is more than 1500. For this one is more than 1300. So we are like, okay, the temperature can be varied a lot. So this one is fixed. And these two will play the game. Okay, so let's try to move a little bit. So this is also from Danish Shenzhen, actually a Russian friend. And the calculate distribution about 2 plus and 3 plus. So this is what we are talking. 2 plus, 3 plus, right? Let's try to note the oxidation state. So this is 2 plus, and this is 3 plus, right? So we are doing that, okay. When we are having a more ratio of oxygen, so we are doing, okay, it's going to be 2 plus or 3 plus. So when we are having like 1/3, there is almost no ferric ions. But when oxygen is higher, so this one will be dominant. Okay, this is the first information. And if we are reading in details, okay, let's try to do it. So we have, this is 1, so this is more rate of oxygen. So this is pure, when there is no oxygen. So this is pure air, Fe. The melting temperature is like 15 and 30. Here is oxygen. So we have some compound. So for example, so we have Sulfide, right? And we have ferric oxide or hematite. This is hematite, Sulfide. What is female? It's magnetite. Fe3O4. Magnetite. Okay. So when we are having iron, so we have Sulfide, magnetite, hematite. Different phases, and it has very strong relationships. For example, when we are having that, is the oxygen potential for copper -6. So what are we having? Dominant, it's going to be female, or it's going to be -6, female plus Sulfide. So this is what we want to have. So we never can see. So this is where we are added. So this is the region. This is the region for copper making. And you can try to plot it with it. So this is where we are making this pilot slag. Okay. So let's try to get a sample. So this is most traditional base diagram for the slag discussion. So 1 part ferrous, 2 plus oxide. And another one will be silica oxide. Okay. Where have we found silica beforehand? In the raw materials. If you are talking about the furnace, we have 4 input, right? So what are they? Concentrate, oxygen, flux, and secondaries. So the flux, we haven't given any definition of a flux. And now I can show the information. The flux indicates to silica oxide. So why we are using silica oxide? when we're going properly some pages, some days ago, when we are discussing about the composition, about our concentrate, what are we having? We have divided into 4 groups. What are they? In the concentrate, what do we have? The concentrate, what do we have? Raw material, good. We have divided into 4 groups. So one is sulfides. Copper, iron sulfides, right? And the
Yes.
second group will be,
Sulfides.
sorry, associated PGMs, treasures. And the third group will be some toxics, arsenic, mercury,
Oh, yeah.
something like that. How about the first one? Gangues. Gangues. With sulfide particles will have contamination in the middle. So this is the gangues. And in gangue components, this one is the biggest. For gangues, we have silicon oxide, right? Calcium oxide, aluminum oxide, magnesium oxide. They are gangues, but the silicon is the biggest. So when we are having the biggest one, we are taking that as our first option. First option. Okay, so this is iron oxide. This is silicon oxide. So same story. So this is more vivid, more vivid. So this is fully melted region. So we are having fully melted slag here. And in between, so this is a binary, two components, iron oxide, silicon oxide. And in this binary system, there is one stoichemic compound. So this is biolite. We want to talk about biolite. It refers to 2 more ferrous oxide
Oh,
and 1 more
silicon.
silicon oxide. So this is biolite. Biolite. So this is a mineral. It's mineral. And you are getting XRD peaks. So this is biolite. And this is a major component in the slag phase. This is a major in the slag. So we are having this having name of biolite slag. So this is biolite. So we are knowing, okay, the melting temperature for this one, ferrous oxide, is 1389. So something like that. And we are having silicon oxide. The melting temperature is 1713. So 2. But the lowest temperature when we are getting liquid will be around 1177. So that's good. Reasonable temperature for us. But the interesting part will be when we are having this one, and when we are talking about slag, the most important indicator will be iron silicon ratio. I will put it here. Iron silicon ratio. The percentage of iron, elemental iron, and the percentage of silicon oxide in the slag. So this is 1.86. So this is the one here. This is the one here. This is biolite. Biolite. And when we are starting that, interesting part will be we will have 2 directions. Or originally we are somewhere here. We have a lot of iron oxide because we are starting from carbohydrate. Iron will be oxidized. So we are only having large amount of iron oxide, and we have very small amount of
Silicon.
associated with the concentrate, right? So if we are not adding anything inside, so there's only small amount of silicon, but large amount of iron oxide. So we will be somewhere here. We agree? Yes? And when we are having more silicon oxide as flux, we will move into this direction, the right direction. So the liquid dose temperature will be decreased. So this is magic. This is the strategy. We are using this one to reduce the liquid dose temperature. And the question is coming. So when we are moving from this part we are taking a very low temperature here, and it's going to be larger. The mole ratio of firelight is 1.86. So how about this point? The ion silicon ratio will be larger or smaller?
Larger.
The ion to silicon ratio in this point is larger than 1.86 or smaller? Larger. This is larger. Do you agree? Yes. Is it good? So this is larger. And we have lower temperature. Sounds good? Sounds good. But if I am telling you that, when I was an undergraduate student, all the copper smelter in China, all over the world, they are using somewhere here. They are not in this part. They are moving to this side. They are moving to this side. They are not moving to that part. And recently, we are moving from this side to this side. And we are still not in this part. Actually, there are two values, right?
Yes.
Two values. So this is ideal one. But we are not taking this one. We are taking this value. And we are keeping the precision to this part. And we are very carefully moving to the heat. So this is the reality. So what will be the reason? Or if we are keeping the precision here, we are having a smaller ion to silicon ratio, right?
Yes.
In the past, ion to silicon ratio actually 30 years ago, 40 years ago, it was 0.7, 0.8. So it was like half of that. What does it mean? Well, we are having ion to silicon ratio like 1.8, and if we want to have ion to silicon ratio that's 1.8, we need double the amount of silicon in the slab, right? So when we have, for example, when we are having like 100 kilogram iron, and you are adding like 20 plus kilograms of silicon oxide, you are having 100 here, and you are having like 100, like 50 plus kilograms of silicon oxide. You are having such a ratio, right? But if you are having 100 kilogram iron oxide, you are finding a number 0.8. The silicon will be more than 100 kilograms, right? So which means you are adding a lot of flux into the system. And this is what our, probably not ancestors, but our former engineers, what they were doing. And the researchers are following such a strategy. So the reason is a good question. The reason is a good way in learning something. Okay. So this is, have you got my question? Or have you got this part? No? Or yes, no? Okay. As I mentioned, in the concentrate, after oxidation, the precision will be somewhere here. We have very large amount of iron oxide,
Yes.
very limited amount of silicon oxide. So this is the starting phase. And if we are adding flux in the form of silicon oxide, we are decreasing iron silicon ratio, right?
Yes.
So we are having lower temperatures. So from theoretically, this one will be an ideal one. Lowest temperature and before the increase of temperature, and we have reasonable iron to silicon ratio, right? This is an ideal point. But the reality is that we are not making our production with this point. We are moving to this side. We are moving to this side, which means we have to add more silicon oxide. In the past, the iron to silicon ratio was 0.8 or 0.7. And nowadays, it's like 1.3, 1.4, 1.6, or 1.8. So we are pushing. This is a value, right? A value. This is a value 2. This is the value 1. So we are staying in value 2. It's very interesting. Actually, when I was having such thinking some years ago, 10 years ago, actually, if we are reading the figure upwards, what we are finding? We are finding if we are starting from this side, and if we are decreasing the amount of silicon oxide, or we are decreasing ion silicon ratio, increase ion silicon ratio, we are having ferric ions. If you are in value 1, you are having larger amount of ferric ion. And if you are in value 2, very small amount of sulfuric oxide. So when there is no very small or very small amount of ferric ion, you are having very little magnetite. So we are having dominant ferric oxide. Okay, let's try to make a summary. Ferrous oxide is our ideal ion product. Ferric ion is annoying. And we want to keep a small percentage of ferric ion in the form, in the system. So this is why the industrial practice gave the precision somewhere here. Okay, so this is information I want to tell. And besides this region, and 1178, 1470, 1600, 1700, they are different crystal structure for silicon oxide. Alpha, beta, and you have different crystal structures. Oxide doesn't matter. And we are only using chemical system here. So this is very interesting part. So actually, after several hours introduction or discussion, and you probably have already drawn the conclusion. Professor Xia is always talking about the harmonies of magnetite. Is always talking about the negative effect of ferric ions. So this is my thinking. This is my concern, and it should also be your concerns. Ferric ion and magnetite. They are something we are fighting. Okay. So there are some other stories. Same story. A lot of old research, 1970s, 1960s, 1950s. The binaries. Same story. The melting temperature. This is similar. And for the ferric ion, so this is experiment. It's not easy to have such methods. So you are knowing that when you are writing some furnace at 2000, it's very critical in the past. Because the heating system, the furnace or the refractories is the problem. And nowadays it's easier for us to push the furnace to high temperature. So if we are having a select system, let's fire that on the blackboard. I was telling about we should have an X here. The X indicates we have this one and we have this one. So let's try to read the phase diagram. 1, 2, 3. Are you familiar? So same with that one, right? So this is the ternary phase diagram. So let's try to check. The behavior of this phase diagram. But I don't like this one. So Fe plus as silica. This is not a proper form of silica ion silicon ratio. This is not proper one. And if we are referring to ion to silicon ratio, it should be silicon oxide. But this is the original phase diagram. We picked it up from a reference. So if this number should be divided by 2, SiO2. Actually, this is 28, and for silicon oxygen, so it was 32. So like times 2. So 1.5, 1.5, 9. So this is 5. So this is 5. So this is smaller. This is larger. So this is where we are stopped. The industrial practice is going on in this part. And this is ideal part. Ideal part? Okay. So this is first information I want to clarify. And besides ion signal ratio, let's try to read the other nice or properly ubiquitous surface. So this is 1. So this is a closed region. Closed region for this one. So it was referring to liquidus temperature for 1200 degrees C, which means at 1200, when you are in this region, you are fully melted. You are fully melted. If you are outside somewhere, sorry, you are getting solids. You are getting solids. So this is fully melted region for 1200 degrees C. And if you are in this part, so you are getting some liquid, and you are getting this one, a solid. And if you are in this part, you are getting sulfur oxide. And if you are in this part, we are getting magnetite. Okay. This is for 1200 degrees C. And another one, another big circle. So this one is for 1350. So higher temperature, you are having larger region, a larger window. So if you are an engineer, which one do you prefer? Engineer. If you are working very close to furnace, if you are an engineer, so which temperature window will be your choice? Sorry. Last window. Okay, very good. Reasonable. If you are an engineer, you should keep the furnace hot, right? So the work should be carried out properly. So I should be very safe. I should be very safe. So if I am having a big window, which means I'm very flex, I'm very free. I can be here, I can be here, I can be here. So you have a lot of freedoms. A lot of freedoms. But my following question will be, if you are the boss of the smelter, which one are you going? Small one. Have a hand. Ewan? Have a hand. Yes, I am pushing my employees to decrease the temperature of the furnace, which will save my pocket. I'm not burning my money, right?
Yes.
Because I'm protecting my furnace as well. So this is different part. How about the third question? If you are a technician, if you are technical people, what should you do? Smaller one. Even the initial point. Find it, and we are making strategies. Okay. So this is liquidus temperature for this system. And besides the liquidus temperature, besides ion ratio, another important line, it was oxygen potential. Oxygen potential. And you are knowing that we have already discussed. When you are producing copper, when we are producing copper, the oxygen potential will be -7, -6, -5. So they are our options. So if we are having such ones, you are finding that the oxygen potential should meet my requirement. The liquidus temperature should meet my requirement. These two should match. When you are having these two, you are running the furnace with melting slag, and you are getting liquidus copper at the bottom of the furnace. Otherwise, you are losing something. Either the slag will froze, or you are not getting copper. You are getting something else. You are getting oxides. You are getting sulfides. So you are not having that. So these two should match very well. So if you are having such oxygen potential, so this is the tendency. So if you want to have -6, -5, you are somewhere here. Okay, so let's take 10 minus 7 as an example. So this is a line. So it will be outside of 1200 degrees C. What does that mean? This is not our option anymore. So we have to push it to 1300 or something else. If we are having 1350, so we have big regions, right?
Yes.
Big regions. But as we have already mentioned, if we are having this simple ratio, so if we are having small amount, so this is a liquid dust, so this is the boundary line, right? Actually, this is a liquid dust for 1300, so we have very small region here. So if we have this one, but if we have this big anisotropy ratio, we have a bigger one, right? Bigger one. So this is something we are discussing. So anisotropy ratio, temperature, oxy potential, they are most important parameters for slab. You are writing right on your slides. Oxy potential, temperature, and separation. They are most important properties or information about our slab. Okay. So this is what I want to talk for this part of this diagram. And if we are pushing a little bit more. So here, first of all, I try to read from here. So we are I'm not using FeOH. We are using FeON. Right? So this is a ternary phase diagram. And silicon oxide is here, iron oxide. And we have another one. Calcium oxide. Again, this is a ternary system, right? But this is the fake one. This is the fake ternary phase diagram. Because we have put 2 here. We have put 2 here. So this is ferrous plus ferric. So we have put 2 components here. So this is the fake ternary. It's a quaternary actually. But if we have 1, 2, 3, 4, if we have a quaternary, we are not checking. It's not visible with 2-dimension versions. We cannot check it, right? So we are making some, let's say, transmission. We are making some magic here. So we have put 2 there. And if we are having 2, I have the same ratio. So this is a 1. We are doing very well. So fire is here. And there's another unstable component. One more and ferrous oxide, and one more silicon oxide. So the anti-silicon ratio is 0.9. And why are having this 2? Originally, actually I was telling about anti-silicon ratio. In the past, our engineer would like to have this part, right? A smaller anti-silicon ratio. And another story is that in the past, they would like to put certain amount of calcium oxide as well. So they are adding flux. The flux has 2. One is silicon oxide, another one is calcium oxide. So they are adding both of them. And the reason can be found from this diagram. So if you are checking from this, so same story, let's try to check. This one will have the melting temperature 1205, melting temperature of violet. So from these 2 sides, it will decrease a little bit. And for this part as well, we have already built out the information. And if we are checking the liquid dust, what we are finding? We are finding some interesting stories. First of all, the fourth part, the highlighted region. On the slide, what we are checking. So the lowest temperature will be around 1000 degrees C. Around 1000 degrees C, or it was 1100 degrees C. Or 1000 plus. So what does it mean? It means in this region, the melting temperature of the slab is even 100 lower than cyanotic band slag. So if we have this one, sounds good. So if you are moving to this part, you have small and silicon ratio, and you have like 20% calcium oxide. You are very safe. Temperature is low, and ferric ion is small, right? So this is the reason. This is the reason. Okay, we are having 10 minutes break, all right? So we are getting coffee, you are getting water, and you are getting some smoke. That was the color of the break. Okay, actually I will type a message for them. I'll try to tidy up my thinkings. Okay, let's go back to our ternary phase diagram, and it was called a fixed ternary or an ideal ternary phase diagram. So we have two components here. So this is where our former industrial slag system, and they are using small iron to silicon ratio, and they are adding calcium oxide. So this is what they are doing. So originally, again, let's try to make a story and try to develop this strategy together. So originally, when you are having concentrate oxygen supply, so the iron will be oxidized to this one. So it was ferric and ferrous together. All of them will be here. And there will be small amount of gangues containing silicon oxide and also calcium oxide. So it will be somewhere like this. So probably somewhere here, here, smaller, somewhere here. We have more silicon oxide and a very small percentage of calcium gangues. So this is the nature. This is nature. And for our ancestors, they are knowing there is this is the safest region for the slag. Temperature is low, and when we are having such a position, so what they are doing, they are adding silicon oxide. So the iron to silicon ratio will decrease. And also, they are adding calcium oxide and get the proper composition here. So this is the strategy. And the problem nowadays, we are no longer using this part. We are moving back to this region. So from here to here, on our ternary phase diagram, this is a very small change. But our engineers, they have spent more than 30 years in covering such a small gap. Very small on phase diagrams, but it takes 30 years to meet this one, or to build this one in practice. The problem or the reason of starting from this region and going back to here, the problem is that we are not using calcium oxide anymore, because the price of calcium oxide is like 8 to 10 times more expensive than silicon oxide. So this one is quite cheap. In the river, you are getting very good purity silicon oxide. But for calcium, no. But in Indonesia, you have a lot of that. So this one is more expensive. And if we are moving back from here to here, and we have made calculations, when we are having larger iron silicon ratio, we are adding small amount of silicon oxide, which means the total amount of slag will be smaller. Smaller amount of slag, and we have less expense on flax. So this is the reason why we are going back to this part. A small slag amount and a short account of the cost. Okay. The summary of the slag. Let's try to make some discussion summaries. So first of all, the slag is the melting or softening. Softening is better. So prefer to make some corrections here. So try to delete melting to softening. Softening. So try to help me in editing this one. Let's do it together. Probably it's a good idea. So let's try to make there's no softening or melting. It can be SOFT, softening. Or softening. Softening is good enough. So you are knowing the meaning now? You know the meaning now? So when talking about melting, we are referring to some compound. Blanching.
Blanching.
Suggestion? Softening.
Softening.
Sorry. Softening. Okay. Okay. I'm putting it here. Good. This is a beautiful my broken English. Softening. Sounds good. Okay, thanks for the correction. Blanching. Softening. So we're talking about melting, like carbon. Sorry, iron will melt at 1531. So it's a fixed value. And for water, the melting temperature is 0. But for slag, there's no melting temperature. No melting because the conversation varies. And also, there's no specific melting temperature. It will become soft. So it's solid, and it will get soft and fully melted. So it was sharp, soft, and melted. So this is stepwise melting. So the softening temperature should be 100 lower than the slag temperature. What does it mean? It means when we are having some slag, the softening temperature is 1100. So we are running the furnace at 1200. So we have 100 safety range that keeps the slag fully melted or kept very well. And the viscosity, it should look like the video you have already enjoyed. So it should be nice going. And for the gravity, it should be smaller. It should be smaller, which is easier for the separation of the slag and mat. And the last two. First one, solubility. So slag is an oxide, right? The oxide, when we're talking about mat will have some percentage of oxygen. So you are knowing that. And also, when you are having oxides, it can also dissolve some sulfide. So the solubility of mat in a slag should be small, and also the copper as well. And the corrosion. Actually, some years ago, when we were having some discussions internally, and I was making my, sharing, and I told them that for metallurgists, for the people who are studying CSU, we are scientists. Yes, we are scientists. What we are doing, we are inventing some systems. We are inventing very, extreme conditions, like HAPO, high pressure accelerator. So in the HAPO process, the high temperature, and you have high concentration of sulfuric acid, and you have even pressure. So all those extreme conditions has been merged, combined in one process. So you are having that. And for us, we are offering high temperature, 1200, 1300 for iron steel. We are running to 1500. So high temperature, and also we are using enriched oxygen. So they are extreme conditions. And for hydro or for pyro, we are offering such extreme conditions. But there is always a need. When we are having such very strong conditions for reactions, you need a container. Always. So if you are making a metallurgical reaction or process, you always need something to support it or try to hold the process. So it was the reactor. So for HAPO, the reactor is a problem. You know that? What's the mining material in the reactor? Do you know that? Titanium, or lead. So they are manufactured in China and transported into Indonesia. So they are very, how to say, inert in the conditions. And here, if we are having metal phase, right? Sulfide phase. If you are talking about the slag, oxide phase. So oxides, sulfides, metal, and gas. So 4 different phases. They are in same reactor. So the refractory will have very strong examination test. So the corrosion is a very big problem. So this is why the boss, the technical people, researcher, want to lower down the slag temperature. So when we have low temperature, this one will be definitely salt. So okay. So let's try to have some industrial slags. So this is a good summary. Case 1, case 2, 3, 4. And there are abbreviations in parentheses. Out of that, flash. Inco, flash. Miranda. Actually, it's the past smelting. And the last one,
Mitsubishi.
Mitsubishi. So you are having the case 4 and case 1 now. So you have talking about slag. Okay, let's try to read. I have already highlighted with colors. So first of all, the most attractive one. So which one is most attractive? Which one?
Flash melting.
Copper.
Right.
Money is important.
Yes.
Money for engineers. We are researchers, we are engineers in the future, and this is our process. And the process should be money to the company, to the people. Copper is our package. Actually, I'm not talking about the whole money, I'm talking about the process. So when we are having such big values, so the cut-off rate of copper ore is only 0.3, right?
Yes.
In China, it's 0.2. So they are copper ore. So this is why I would like to say copper content is most important. Here, so besides copper, here 0.5, 0.6, 5%, 0.5%. Big ranges, 10 times larger than the others.
Yes.
Right?
Yes.
So what's the reason? Why? Why such poor hypothesis? Why such poor technology is still used? If we are losing 5% copper in the slag, the technology is no longer competitive.
Yes.
Right? What's the reason? What's the reason?
Because it's to oxidize.
To oxidize. Good. Very good. Sorry. This is the reason. Actually, I'm going to get closer to the reason, and I will explain later. So besides copper, so what is the second most interesting part?
Iron.
Magnetite. Good, magnetite. Okay, magnetite. 1, 2, 3, 4. Okay, let's try to keep magnetite for a while. Let's try to check iron first.
Yes.
So case 1, iron, 38. Case 2, 39, 38, 37. So let's try to draw a summary. Let's try to draw a summary conclusion. The iron content in a smelting slag is always some numbers very close to 39, 38, or 40. So the iron content like 40% in the slag. So this is universal. Or this is formula for the processes. But among the iron content, there will be two different forms. Two different forms. So one form is magnetite. Another one will be ferrous oxide, but ferrous oxide is not in such a form. It will be in such a form, in final form. So iron will be here and here. Now this is ferrous plus ferric. Okay, so let's try to check. We have same amount of iron in the slab, but for magnetite, 11%. And so this is how much iron is here? Elemental. Calculation first, please. Calculation fast. What's the number? 3/4 of this value. 3/4, like 8%. Right? Can someone give me an accurate answer? 72. It should be larger than 72. 72. What is that? 78. Actually, I prefer to agree with 78. Because this is 5 more iron, 4 more oxygen. So this is 64. And this is 53 times 3. So like 3/4. 3/4 times this one is like 8%, around 8%. So 78. So 78 is iron, right? Right? Okay, attention please. So if we are having 78 or 8% iron here, so total amount 20% of iron is in the form of ferric. We agree. The 20% is in this magnetite form, and 80% is in ferrite form. So this is for one slab. How about the second one? Same story. How about this one? It's much larger. Much larger. And for this one, it's like more than 15, and here it's like more than 40%. More than 40%. Difference is coming, right? So someone is giving an answer over oxidized. Actually, the ratio between this one and this one can be an indicator of oxidation. If you are having pure ferrous oxide, it was reducted. When you are having pure magnetite, oxidized, and copper will be in the middle. The middle is range. The range. So this is magnetite, and for the last one is sulfide. It's lower, right? It's lower. So this is why this is very good technology nowadays. So this is actually from China. This is from Inco. Used to be from Canada. The red map actually is used from South America. South America. And this is from Japan, Canada, Indonesia. So actually, besides copper and iron, they are dominant ones. What will be the third interesting element here? Which one? Sulfur. Sulfur. Okay, let's keep sulfur for a while because we are starting from concentrate. The major elements will be copper, iron, and sulfur. So this is the one. So let's try to keep sulfur for a while because the number is small. Let's try to start from silver oxide. Silver oxide. And here, the iron is around 40, silicon is like 30. 37. 20. 30. 30, 30, 37, 20. Range is a lot, right? Range is big. It's big. If we are going back, which slide can give the reason? I find that. So the iron silicon ratio will play a role here. So if we are calculating the iron silicon ratio, here is 1.28, here 1.1, 1.6, and 1.1. So we are keeping a smaller iron silicon ratio. And this one over oxidized and with big iron silicon ratio. So two negative factor. So they will push the situation to poor side. So we are having lots of one over here. Okay. So besides silicon oxide, so if we are reading sulfur 1.2, 1.1, 1.7, and here actually it was not examined. Not actually no result is presented here. But here 1, 2, 3. So we have the conclusion. We are also having sulfur in our slag. So when you are having some slag in ambient atmosphere at high temperature, you are also smelling something. Sulfur dioxide is quite sensitive. Okay, sulfur. So sulfur, and after that we have gangues. So this is zinc, calcium oxide, gangues, right? So this is from the concentrate, gangues. And for the Miranda, what we find? What means sewage? Calcium oxide? 7%. And this technology is from Japan. And this is not from the concentrate. This is from the process. This is from engineers. They are adding calcium in the system, but calcium is not added in the smelting stage. It's not here. Not here. And we have already warmed up our how to say material streams. So when we have one furnace, 4 incomes or inputs, it will be concentrate, oxygen, flux, and secondaries. So in secondaries, there's one type. It was a slag from the next furnace, the following furnace. So it's from the converting furnace. So the converting furnace slag will be returned to the smelting furnace. So in that furnace, in the sewage was adding a lot of calcium. So that slag has brought calcium here. So this is the reason. Okay. So this is an interesting part. And in the future, when you are knowing the composition of the slag, you will have first impression on the process. Whether they are behaving very well. So what will be our objectives here? We should lower down this one. We should lower down this one. We should increase this one, right?
Yes.
So if we are increasing this value, the volume of the slag will decrease. If we are lowering down the temperature, we will have smaller energy consumption. We will have better lifetime of the furnace.
Yes.
And if we are having smaller amount of copper in the slag, we are having better recoveries. Sounds interesting? Okay. As I mentioned 1 hour ago, you are having some assignments, but it's not a mandatory. So if some of you are interested, you have 3 copper smelter nowadays in Indonesia, and you can find 1 partner. So 2 students, you can be a pair. And you are finding out the process of 1 copper smelter in Indonesia, and try to Google or try to search their processing parameters, especially the slag. Okay? So you are knowing the process. And after this course, probably you will have very detailed survey about the copper smelter. And if in the future you are the engineer, or if you are the CTO of the smelter, it's going to be nice. I am studying that some years ago. Okay, this is I think this is an assignment. If you are interested, you can start such a work. And there can be some kind of, not adding ones, some bonus after this course. And I will evaluate, and I will try to review your writings. And I will, good, actually you have 60%, right?
Yes.
Of daily behaviors. So this will be in part of it. Okay, this slide. So let's try to read this figure again. So you are knowing that. So you are knowing that. So we have two important starting points: the pressure of copper and iron. And we are moving between this range. So where is our map making? Where is our map making? Our map making is somewhere iron is partially oxidized. Right? Partially oxidized. We are still getting some iron in sulfide form. So if iron is partially oxidized, so it will be on the boundaries. It will be on the boundaries. So we will be somewhere here. So this is map making. Map making. So this is where we are stopping. And actually, it's very interesting knowledge. It's just the boundary of clear? I just think we have a very good boundary. So this is why we are making matte. If we are pushing a little bit more with the problem, it's going to be dominant for iron oxides. So we have no solutions so far. Or we have solutions, but they are not economic boundaries. So the boundaries, interesting. So the thermodynamic is very important. And if you are getting closer to the process, you are getting the resource. And you can offer solutions in the future. Okay. Can we move to the sub chapter? Subchapter is talking about the materialism. We are knowing, we are starting from carbopyrite, from concentrate, and we are producing our slag and matte in the furnace. But we are starting from a floating concentrate. And in the minerals, we are having carbopyrite as an example. The first one, actually, we are having this 4 inputs. When we are putting this carbopyrite in the furnace, the first stage, this reaction will happen. The illustration or decomposition. So those minerals, they are ternary, even quaternary. They are complex compounds. At high temperature, what they are doing? They become simple sulfides. So this is nature, this is chemistry. So for example, carbopyrite at high temperatures, what are we having? We have elemental sulfur, we have chloride, CO2s, and we have simple nickel or iron sulfides. If we are having some contaminations, gangues, like carbonate or silicate, they are also decomposing as well. So this is what we have been found, what we found. And there's one claim, there's one solid conclusion. So when we have iron here, and we are having this dissociation at high temperatures, there's one interesting story for copper. There are options. It can be 1 plus. It can be 2 plus, right?
Yes.
So for 1 plus, it will Cu2s. For 2 plus, Cus. And for those transmitting elements, and so does probably iron. Without any oxidation, it also has, I will put 2 plus, 3 plus. And at elevated temperatures, there is a solid composition. Without oxidation, those lower oxidation state will be more stable. So when we are having that at high temperatures, when we are having the oxidation reactions, they are the product of the reaction. So this is the conclusion, and this has already been proven several times. So this is something you should know. Actually, I have put here, low oxidation state compounds are more stable at high temperatures. Actually, I want to have one story now. Are you tired? No. You are quite eager in getting something. Okay, one very short story. Actually, 4 years ago or 5 years ago, one student from my team, he was seeking for master's degree, and he was also studying copper. And I told him that you are putting the copper in a furnace, and you are injecting nitrogen, and you should pour out the sample at 1200 degrees C to get our samples. Actually, my instruction, my comments have been given, and he noted of receiving. But in the afternoon, when I was checking the sample, and I saw that no, the sample is not a metal, it's an oxide. It's an oxide. And I told him that you are picking up the copper from the furnace with the protection of nitrogen at 1200 degrees C. And I asked him, what's wrong? What is the reason why we are not getting copper? We are getting something else. Actually, he was a little bit nervous. And I told him that, I'm sorry, Professor Shah. I was hungry. I go to the canteen for lunch. And the furnace temperature dropped. And when I was in the lab, the furnace was at 800 degrees C. And I poured out the sample, but I didn't stop the nitrogen gas. The gas is still nitrogen. But the furnace is on. The temperature is not at 1200 degrees C anymore.
Yeah.
So actually there's very small difference, right? Only some millions behind my lab. And I have a conversation with him, and I asked, and I made a conversation, and I told him that this is not a bad thing. This is not totally wrong. But I would like to have your thinkings. So what have you found? What have you concluded after this experiment? Actually, he became more nervous. And he was hypothesizing that I will give some my criticize. No. So what will be your hypothesis? What's wrong? Same story here. If we are holding the sample, copper, at high temperature, for example, 1200, and when we are having nitrogen gas, the oxygen potential and temperature will keep the metal at elemental form. So it's a piece of metal. When you are lowering down the temperature, the oxygen potential is still the gas, -5. But lowering down temperature, the gas will become more oxidative. So the metal will be oxidized. So this one is simply this one. Low oxidation state is more stable at high temperature. When the temperature drops, it will be oxidized. Okay. So there are two methods for oxidizing some metals. What are they? If you want to oxidize some metal, what can you do? You are oxidizing it directly with oxygen, with air, with some other oxidant. And another way, you are lowering down the temperature. It will also be dynamically oxidized. Okay, so this is a good story, and you are not nervous, but you are picking up some information. Okay, so low oxidation state is more stable at high temperatures. And if we are checking the principles of copper. So copper pyrite is our starting material. So this is the overall reaction. Very simple. Very simple. But human beings covered this one, I think, around 260 years. To try to, this reaction is known 200 years ago, that we are studying it all the time in the past 20 years. Try to get it better and better. The overall reaction, so if you have such a chemical reaction formula, what kind of very short summary you can draw for copper making? So what is the core information? What is the core criteria for copper making? So can you have a try? You have 1 minute to have discussions. So what kind of criteria, what kind of description you are going to make for copper making with the leading of such a chemical reaction formula? Okay, I have a very interest of your name, our coffee boy. What's your name? 坚持好。English, please.
John.
So what is your answer for this question? Some other? Some have hands? Okay, the third boy, please. Eddie. His name? Annika. Annika. Which one? Annika. Okay, Annika. So what's your answer?
Dengan saya belajar tiap malam.
Itu kan yang ada itu di sebelah.
Wow. What's your answer? So what kind of description, summary, thinkings you can draw with this overall reaction? Copper is produced by oxidizing sulfide minerals. That's all. Copper is produced by oxidizing sulfide minerals. So this is why we are taking copper as the example of the sulfide mineral process. Okay. Oxidizing this one, but the red part will be slag. The slag is more complex than the metal part. Okay, the principles for copper making, especially for metal making, there are some fundamental criteria. First one. First of all, we are knowing that carbopyrite, those complex sulfide, they will decompose to simple ones. Simple ones. Iron will be in FeS. Copper will be in Cu2S. And we have two options. And two boys, there's one girl, oxygen. And oxygen will go for iron sulfide. So this is separate. So iron sulfide is preferred oxidation. So this is the first fundamental one. And secondly, let's go back to the previous slide. So this one is preferably be oxidized. So this is why we can put our boil for mat making. Otherwise, this one cannot be enriched. This one cannot be removed. First one. And the second one, if we are moving from this range, the second one, by oxidizing this guy, we are getting copper. For example, if we are oxidizing iron sulfide, can we get iron?
No.
Thermodynamically, yes.
Oh.
But practically, no. So this is the theoretical window. So copper sulfide, by oxidation, we are producing copper. So this is the second one. Let's go to this one. And the third one, slag, mat, slag metal, merchant solubility is small. Because we have two layers. Slag, mat, slag metal. The solubility in each other is very small. Otherwise, it's going to be a mess. A mess. Okay. Okay. So dissociation reactions, we are divide this overall reaction into steps. So those dissociation reactions, smaller ones, carbonate. Actually, this is what we are having in between. And for the preparation oxidation of iron sulfide, as I was telling, copper sulfide, iron sulfide, oxygen. Oxygen will go for iron sulfide. But if unluckily, copper sulfide is oxidized, the copper product, copper oxide, can be sulfurized by remaining iron sulfide. So the copper is a rubber. Copper is a rubber of sulfur. Iron is a sift for oxygen. So one is strong with sulfur, and another one is close with oxygen. So this is having very strong chemical reaction tendency. And for the separation, actually the slag has such a phase, such components, very multi-diverse components, and the mat is the one. So the mat and the metal phase and slag phase are not mutually soluble and are separated. They have different gravities. So this is nature. This is actually, we are having another discussion. On Earth, when we are doing such a separation, the gravity will be a help hand for us. The denser one will be at the bottom, the lighter one will be on top. If we are going to the space, if we are going to the moon, what should we do? If in the future you are doing some space metallurgy, there's no gravity anymore, no very small gravity. What should we do? Okay, keep your mind thinking. In the future, probably you will be the leader of some project doing some space metallurgy. There will be no gravity, and the separation will become a problem. Okay, this is what our mission today. Okay, I think I will try to stop today here, and the following section will take another minutes. Okay, see you next Thursday. Okay, all right.
Thank you, Lao Shen.
See you.